Good evening, everyone. This is Dr. Joanna Wu from the Trottier Observatory and Department of Physics at Simon Fraser University. So, with me today are my assistants Zena, Matthew, and Sarah, who will be answering your questions in the chat box. So those of you who were waiting for the stream before the stream started, we only just enabled the chat function just now, so you'll probably have to refresh your screen in order to see it. So if you'd like to ask any questions, please go ahead and ask away. And I will look once in a while to see if there are any unanswered questions in the chat, but most of the time I'll probably be fiddling with the camera, the settings, the live the camera settings. So I may not be able to see your questions right away, but that's why my assistants Matthew, Zena, and Sarah will be helping to answer your questions. The three of them are very experienced with Starry Nights. They've done many Starry Nights events. They're experts in astronomy, and they will be available to answer your questions. So here is the website for the Trottier Observatory, so you can see the science courtyard. This is our web page. You can actually see right now live on your screen. Let me see. Live on your screen, the three webcams that we have looking at the observatory. So this camera here is looking east. That one is the one that's on the bottom. And where's the one looking west? This is the one looking west, and you can see right there, this little dot here, that is the moon. You can also see in the western sky that the sun has set already, but the sky is still very bright. This is because we are in Canada, and I know there are several people tuning in from other parts of the world. And here in Canada, in Vancouver, we're at a latitude of approximately 50 degrees north, and that is far enough north that the sky doesn't get dark till like at least 11. It's pretty crazy. In fact, even around the end of June, around June 21st, we actually don't get nighttime for about 3 weeks in the year. It's pretty crazy. We get astronomical twilight for about 3 weeks, but we don't actually get real nighttime. We are that far north. Okay, so I have introduced my assistants. Thank you very much for your help, by the way, the three of you. And I'll introduce myself as well. This is me, Joanna Wu. I'm a faculty member in the physics department at Simon Fraser University. This is my, if you click on my research site, you can see a little bit more about myself and what I do. My research is on galaxies. I'm an expert in galaxies. I also do, because of the nature of my work, I also do know a little bit about star formation as well as cosmology, because galaxies is it's a field that spans kind of the whole gamut from star formation all the way to the big universe. Today, I know you're all waiting to see the comet. The comet is really spectacular, and it looks great through this telescope I checked a couple nights ago. However, as you can see, the sky is still really bright in the west right now. So we're not going to look at it first. We're going to look at the moon first, and perhaps by around 10:30, which is 25 minutes from now, we'll be able to see the comet. Okay, so we can, the comet does appear right now. I did check just now. You can see it, but you can hardly see, just barely, because the sky is still really bright. So let's look. I'm actually pointed at the moon already, so let's take a look at it. Whoops. The moon has moved away actually a little bit. The telescope follows the stars, but the moon actually moves slightly relative to the stars because the moon is orbiting our planet around the planet Earth. So this is the moon. The moon right now is in the crescent phase. It's a waxing crescent. Now, waxing means it's getting bigger. So it's just past the sun, so it's moving towards the east, and it is getting bigger and bigger. So right now it's a crescent, and in the next few days you'll see it get bigger and eventually become a full moon, and then it'll eventually become smaller, and then you would call it a waning crescent. So waning means it's getting smaller. So right now it's a waxing crescent, and actually the crescent phase is the best time to be looking at the moon, because when it's the crescent, you can see shadows that the craters make with the surface of the moon. So you can actually see lots of detail with these craters. So I think it's really cool. I think the crescent moon is about the right time to be looking at the craters. In fact, if you use binoculars and you want to look at the craters on the moon, the best time is around crescent moon. So, and the best place to look is right along the line between the dark and the light side of the moon. So you can see that the shadows make the craters a lot easier to see. So let's explore. So our magnification is quite high, so we can't see the whole moon. So let's explore a bit and let's see let's look at some of these craters. By the way, the moon, as we know, is Earth's only satellite. There are planets in our solar system that have a lot more moons than one. We've got one moon, and this moon it's actually quite large. In terms of the ratio between the mass of the moon to the mass of the Earth, our moon is actually the biggest. So it's the biggest moon relative to its planet that it's orbiting. I only just learned that recently, actually. And actually, what's kind of neat, in this particular view of the moon, you can see a couple of these dark spots here that are probably formed from impacts that when the moon was still molten, which eventually melted over and became flat. And actually around here, we're just seeing it right here, is where Apollo 11 landed, about in this area. That's Apollo 11 was when Neil Armstrong and Buzz Aldrin walked on the moon. They were the first people to ever walk on the moon. They landed right there about 21 years ago. It was around July, actually, July 20th or 21st. It was right there, approximately there. I can't pinpoint it exactly because I can't see the flag. We can't see the flag using this telescope, but it was around there. So that's kind of neat. Let's see. Other cool things about the moon that I can tell you about is that the moon has quite a gravitational pull on the Earth. In fact, because of the moon, we have tides on the Earth. So that the tides that come in and out. Here in Vancouver, for example, you can see, and any of the beaches, you can see when the tide goes in and out. And the tides are caused by the gravity of the moon. And it's really neat because the moon, when it's on, it's a kind of a dance between the moon and the sun. So when the Earth is right in between the moon and the sun, that's when the tides are the strongest, as well as when the moon is between the Earth and the sun. So when the Earth, moon, and sun are at a 90-degree angle, that's when the tides are the weakest. So yeah, so the moon and the sun have this interplay that actually has an influence on the tides on Earth. So what else can I tell you? Oh yeah, the moon. What's another cool thing about the moon is that it's exactly the right size to block the sun once in a while. When the sun goes right in between us when the moon goes right in between us and the sun, it creates what's called a solar eclipse. So I don't know if any of you saw the eclipse from a couple of years ago, but I did. I was decided to go see totality, and it was amazing, absolutely stunning. If any of you have a chance to go see a solar eclipse, definitely take it. It's especially a total solar eclipse. So Partial eclipses are fun too, but a total eclipse is a completely different experience, so I highly recommend it. So yeah, it's kind of cool that the moon is just about the right size to block the sun. I mean, the moon does have a slightly non-circular orbit, so it's a little bit of an oval shape of an orbit, so sometimes it's a little bit closer to Earth and sometimes it's a little bit farther. So the apparent size of the moon, sometimes it's bigger and sometimes it's smaller than the sun, but oftentimes it does block the sun completely. So it's kind of a nice little fact about the moon. However, the moon is slowly moving away from us. It's pretty crazy. It's moving a little bit away from us, so that eventually in like a couple 100,000 years it'll never block the sun completely anymore. So but we'll have quite a while yet to see solar eclipses. Okay, anything else that's cool about the moon? Okay, let's see. I'm going to take a look at the questions here. So I think I did see a question that was directed at me. Oh, yes, somebody asked me what fascinates me about galaxies. So yes, that's a very good question. So galaxies are, as I said earlier, galaxies are kind of a bridge between a really small scale, which is the scale of stars, to really large scales, which is like the scale of the universe. It's really hard for us as humans to comprehend these huge numbers. Like, I'll show you, after the comet, I'll show you some pictures of nebulae that are light years in size, or tens of light years, and perhaps we'll also get to look at a galaxy that's 2 million light years away, but it's still in our backyard. So the scale of the sizes is enormous. Like, stars are just really tiny compared to the scale of the universe. But the study of galaxies is something that bridges kind of those different disciplines within astrophysics, because astrophysics has a whole bunch of different sub-disciplines. So little, like, people study subtopics within astronomy. Stellar astrophysics is one of them. Cosmology is another, and they're completely different scales, and people who study stellar astrophysics usually never talk to cosmologists, because cosmologists are the ones that study the whole universe. But galaxy people that study galaxies, have to talk to both of these groups. So it's a nice little bridge. I kind of like it. You have to know a lot about several things. So that's kind of one of the reasons why I decided to study galaxies. Okay, let's take a look. Anything else? So we were looking at the moon. Okay, actually let's explore a little bit around the moon. Let's take a look at some of these other craters. Let's go to the top part here, and there you can see the little point of where this end of the crescent is of the moon. You can see some cool craters. The truth is, I don't know the names of the craters very well. In fact, I don't know any of the craters' names, but apparently they're all named, and you can look them up. There are a bunch of maps out there that name these craters, and you can see some of them. Actually, this one's kind of cool because it's got a little. Actually, a lot of the craters, I've looked at the moon quite a lot, and a lot of the craters have this little lump right in the middle. It's because when something collides with the moon, some little asteroid or meteor or something, it creates a bit of a splash, and the middle bit is one of the after splashes of these meteors that collide with the moon. So there's lots of things, and you'll see that a lot of the craters overlap each other because they're, a meteor lands on the moon and collides with the moon after the other one, and so you'll see lots of this kind of thing if you look at the moon. Let's see, what else can we see here? Sometimes you'll see, I think we're not. Oh, maybe, so I remember at the bottom of the moon, there was this one crater that had rays coming out of it because the debris from the explosion just went all over the place. I wonder if we can actually see it. I think it's still within the shadow right now, unfortunately. But here's another crater with a little mountain in the middle. Isn't that cool? see, what else is there? Yeah, so there's the other point of the crescent moon. That's what it is. And the moon is actually really low in the sky right now. You can see the top webcam there is the image of the telescope pointed all the way almost to the limit of how far it can bend, because it's really low in the horizon. In the middle panel, the webcam here, the moon looks kind of high still, but for the telescope it's really low. So the telescope is bending pretty far. But when any object is close to the horizon, you can see that there's a lot of atmospheric turbulence, because when you're looking through the atmosphere, looking towards the horizon, like if you're looking straight ahead, you actually look through more atmosphere than if you were looking straight up. So if you're looking straight up, that's called the zenith. You're looking at the zenith. If you're just looking exactly straight up, you have a lot less atmosphere to look through. So the moon looks really blurry, like there's a lot of distortion here from the atmosphere, because there's a lot of atmosphere that we're looking through. So that is the moon. What? Yes, okay. Okay, somebody asked about multiverse theories. So there are a lot of theories about why certain things are uncannily just right for things. The multiverse theory is one way to explain the fact that so it's not just the fact that the moon is just right, the right size to cover the sun. There are other things that seem a little uncanny, like the gravitational constant being like not too, if it was too strong, then nothing would, like everything would collapse on itself, the whole universe would collapse on itself, and we wouldn't have planets. If the gravitational constant was too low, then things wouldn't collapse at all. We still wouldn't have planets. Things like that. There are a lot of physical constants that seem fine-tuned. It's actually called the fine-tuning problem. It seemed fine-tuned to produce life, and one of the ways people explain it is with a multiverse, is saying, well, maybe our universe happens to be the one with all the right constants, but there are like many other universes that don't have all the right constants. However, that's a theory that is not provable and not observable. So it kind of borders on, it's borderline non-scientific. So there's some people who work on multiverse theories would argue otherwise, but so far, at least, they're not observable, and they're not falsifiable, which is meaning that there's no way to prove it wrong. And that's something that's really important in science, is if when you come up with a theory, you should have some way to be able to prove it wrong. So far, we haven't been able to test such theories. Okay, let's see, what are we at? We are at 10:18. Okay, I am going to try, let me see, what is the sky is looking a lot darker now in the west. How about we try and turn the telescope towards the comet? Let's try it. Okay. So this is an app called the Sky X. It's really good, but it's not free. If you're looking for other kind of planetarium apps that are free, that are easily installable, I highly recommend Stellarium. It's free, it's open source, and it's got the position of the comet already in it when you download it. I mean, at least the Android app version it's already there, and the web version is already there. If you download the desktop version, you might have to input the comet name and search for it, and then it'll appear on your app. But it's pretty cool. So you can use it to learn the constellation names and so forth. Okay, so let's look for the comet. It's right here, Comet Neowise. It's C2020 F3. Neowise is just an acronym for this project called the Near Earth Object Wide Field Infrared Scientific Explorer, I believe. I can't remember the full acronym. WISE is actually the name of the satellite that observes in the infrared, and NEO is just kind of the thing that was tacked on to distinguish it as the project that's using this telescope. But the WISE telescope is used for many other things. This telescope was used, at least Neowise was the project to look for near-Earth objects. And this is, whoops, here. That is the comet right there. So to be able to see it with your own eyes, I'll just show you, this is the Big Dipper right here. This is the Big Dipper. And the entire constellation is the Great Bear. And the comet is right here. So there's a star. So if you see the cup stars, there's another star here, and another star here, and then the comet is right there tonight at least. So the comet is moving this way approximately every day, and it's actually getting dimmer every day as well. So it's still visible to the naked eye, especially if you're not in a big city. But in a city like Vancouver, it's still kind of difficult to see right now with your naked eye, but it's still possible. You can still see it. Okay, so let's go there. I know you're all waiting to see it. So let's actually take the telescope over there and see how well we can see it. The sky looks pretty dark, so let's take a look. And I'm going to have to make the exposure more like 2 seconds. And there it is. Let's see, let's adjust the image a little bit. And there is the comet. I'm going to move it over just a tad. Move it over just a little bit. And there it is, Comet Neowise. It's not very frequently that we get a naked eye comet come through our neighborhood. It's about once a decade or so. So this particular comet has a very long period. It's something like 6,000 years. But there are lots of comets so in our solar system. So we do see a bright one about once a decade or so, approximately. This one is still visible to the naked eye, but as I said, it is getting fainter. It is yesterday was the closest approach to Earth, and but it's still even fainter than it was a few days ago when it wasn't as close to Earth. So it is getting fainter. So take the opportunity to go out and see it if you can with your eyes. But it's also cool through the telescope. Okay, I'm going to try to adjust this image so we can try to see a bit more of the tail. So last night, or 2 nights ago, it was darker actually. I think I was looking closer to 11 the other night, and we could see the tail a little bit more clearly. The tail should be pointing in this direction, this way. But there it is. So the nucleus is very much like an asteroid, actually. The nucleus is about 5 kilometers in size, and the gas around it that's glowing green, actually the reason why it's green is because it's the gas is the green is from carbon, actually carbon molecules. But the gas around it is called the coma. Coma, actually the word comet is from the same word. It's from Greek. It means hair. Because the Greeks, when they saw comets, they thought of comets as having hair, like long hair. The tail of the comet. Today we just call coma the atmosphere around it. So what is this atmosphere? Like it doesn't last very long. It only appears when the comet gets close to the sun. So normally the gases are frozen in the comet, and it's so they make up a bunch of ice. And on Earth, when you melt ice, it becomes liquid, and then if you heat it up even more, it becomes gas, right? Like water, if you boil it, it becomes a vapor, which is a gas. But in space, so that happens on Earth because we have a really thick atmosphere. But in space, the conditions are such that you actually skip the liquid phase. You go from ice to gas. And that's what happens when a comet goes close to the sun. When it gets close to the sun, the ices, the scientists use the word sublimate. The ices sublimate. What that means is that it goes from ice to gas with skipping the liquid phase altogether. So the ices become gas and form a bit of an atmosphere. It's loosely bound to the nucleus of the comet, but it creates this atmosphere. And that atmosphere gets blown back from the sun. And there are actually two forces from the sun that create the tail. One of them is the solar wind. So the sun actually gives out a wind of charged particles, mostly electrons and protons. So I don't know if you remember in school, but protons are positively charged and electrons are negatively charged. And so this wind comes off from the sun and it moves really fast and causes the gas to also become charged. Now, why does that happen? Because when it goes through the gas, it strips off electrons from the gas. So if you have like a carbon atom, which normally has 6 protons and 6 electrons, some of the electrons might get stripped away, and then that carbon will become a charged gas. It'll become charged, and when that happens, they're called ions if they've got some sort of charge. So the solar wind creates a long tail called the ion tail, which is blue in some of the pictures you've seen. But there's another tail that is easier to see, and actually when the sky gets darker, we'll be able to see the other tail. In fact, I can already see it. The tail. This is the yellowish tail, the wider one. That's the dust tail. That dust tail, you'll notice, curves. So it'll curve. The ion tail in the pictures, we won't be able to see it here, but if you take a long exposure of pictures, you'll see that the ion tail is really straight, and it always points away from the sun. The dust tail also points away from the sun, but it curves. Now, dust is not as easily ionized as the gas, so it's a lot harder to take the electrons off of the dust. So why is there a dust tail then? The reason is because the sun has another force that works on comets. What is that force? It's called photon pressure. It's kind of weird. So I learned this in physics. If you take a physics class, you'll learn about this. It's really weird. So light is made up of little particles called photons. And when photons move, they actually exert a pressure on things. So if you're in your living room, you're looking at your computer screen, the light from your computer screen is actually pushing on you. Isn't that crazy? And the sun, if you're out in the sun is pushing on you. It's actually, of course, you don't feel it because the push is really, really it's really gentle. It's a very, very light. There's no way that we humans can feel it. But little dust particles, which are really, really tiny, they really feel the push. They're so small that photons can push them very, very easily. So that's what's happening with the tail of the comet. The dust tail, which you can kind of see here. We'll see it a little bit better when it gets darker. Maybe I'll even increase the exposure a little bit and see if we can see it better. Not quite yet, but the dust tail it's being pushed away by light from the sun. Because they are heavier particles than the gas, then it's a little bit harder to push them, so they curve. And they curve in the direction that's kind of the opposite of the motion of the comet. So the comet is actually not moving away from the tail. Like it's not moving in the same way that you think. It's actually almost perpendicular right now. The motion is almost perpendicular to the tail, which is kind of crazy to think about. It's really not intuitive. It's like really not what you would think at first, but that's what's happening. So this is the comet. It's so gorgeous. It's so pretty. You know, in ancient times, ancient cultures, in fact, a lot of cultures, and I don't really understand why, but a lot of cultures were afraid of comets. They thought comets meant something negative is going to happen. And I don't understand it because comets are so beautiful, right? Aren't comets beautiful, especially when you can see them with your eyes? It's really amazing. So, so comets used to be omens, and it's really strange that all cultures have had the same fear of comets, but there you have it. Today, at least, I think the comets are beautiful. So, this one you can start to see now. Okay, I'm going to stop talking and I'm going to try enhancing the image a little bit so you can see. In fact, I'm going to start a live stack and I'm going to play with the image here so that we can see more of the tail. Oh, we can already see it better here. The sky is still quite blue, so I'm going to lower the blue. And try to enhance a little bit. And now you can start to see the tail go to the left here. Let's see. Isn't that pretty? Okay. Oh, not quite. Maybe that's a little too overexposed. I'll put this. No, maybe I'm over here. Yeah, you can see the tail is definitely going that way. Isn't that cool? Comets are absolutely gorgeous, stunning things. So, in any case, I've actually seen a few in my life. I remember, so the last naked eye comet was in 2007, but I think I remember it being only visible from the south, like Australia or South America. This one is more concentrated in the north. In fact, in Vancouver, it's circumpolar, meaning it never sets or rises. It always goes around the North Star, and it doesn't actually set. So the comet is yes, I understand that the frames are not getting stacked. It's because there are not enough stars to stack in order to align them. But that's all right because I'm just getting the one image. In fact, I can maybe increase the exposure time a little. Let's increase the exposure, clear, and start again, and we'll just get the one. It's just that stacking is the easiest way for me to be able to fine-tune the colors here for you. Okay, yes, so there were other naked eye comets. It's approximately once a decade. Maybe the last one was 13 years ago. It was 2007. That was more visible in the southern hemisphere. But before that, there were two bright comets, 1 year after the other. So it was in 97, I believe, was Hale-Bopp, and the year before that was a comet called Hyakutake. And I remember seeing them as a kid. Those two were so exciting because they were really bright. They were my first comets I'd ever seen. It was really exciting. And this is I've seen a few through the telescope as well, but this one I think is the third naked eye comet that I've seen. It's really kind of fun. All right. So I'm going to take a look at the chat box. How are we doing? Thank you so much, Matthew, Sarah, and Zena, for helping out with the questions. So, Oh, okay. So is it right or wrong that the gravitational tug or collision sends them out of the Oort cloud and into the elliptical orbit? Yeah, so that's a very good question. So comets are, so scientists think that comets live mostly in this cloud that's way beyond the orbit of Pluto, called the Oort cloud. And once in a while, a comet gets knocked out of its out of the cloud and into the inner solar system, so that we can see it. And yeah, so because we think that there are lots of objects, like thousands of objects in the Oort cloud, or probably many more than that. That's probably the reason when they get close to another object, the gravity knocks it into the inner solar system. So that's probably why, and that's at least the theory as to why comets sometimes enter the inner solar system, and then sometimes we never see them again. There are a few comets that do come around every so often. So Halley's Comet, for example, comes every 80 some years or so. I don't remember the exact number. But yeah, the last time Halley's Comet was seen, I believe, was in the 80s. And that's quite regular. That one actually has been noted throughout history. Actually, there are lots of historical references to a great comet, and it happened, and we know which one it is. It was Halley's Comet. That was kind of cool. Will there be a supernova soon? Okay, so I think maybe now is a good time to move to some of the other objects I wanted to show you. This was the comet. This is cool. Actually, before I do that, I'm going to take a screenshot and save, because this is so cool. And I want, that's probably pretty good, or maybe I should frame it a little bit better. Okay, I am going to close this and take a screenshot of that. It's so pretty. So that was Comet Neowise up close and personal. The green, again, the green is because of carbon in the gases of the star. Is the comet visible from Japan? Well, you'd have to actually look. I believe it is, because I did check recently that it is visible from Hong Kong, so it's probably also visible from Japan. Actually, one of the best apps to check is Stellarium. It's a free app that you can check in, and it's got the position. The web version, at least, has the position of the comet already there. In fact, why don't I just show it to you? This is an app that I use quite a lot when I'm not on the observatory on my own personal computer. So this is Stellarium Web, and Stellarium Web, it'll automatically see, it wants to know my location. I'll stop there for now. You can put in your location, it kind of guessed, and there you go. See, look, it already has Neowise right there. You have to zoom in to see exactly where it is. But I think it's referring to this one? No. Is it referring to this one? Wait, it is, just a second, you have to hop from here to here, it's down here. Is it that one? No, which one is it? Is it this one? Yes, it's that one. That's Comet Neowise. So yeah, so take a look at that. You can, there's the web version, and look, and there's a satellite going right across as well. So it's pretty cool. I recommend it. Okay, so enough of Stellarium. Let's actually look at the comet again one last time. And there it is. Actually, I'm going to stop the live. And this is a lot less adjustable. Actually, I don't know if you've been paying attention, again, the telescope is following the stars, but the comet is moving relative to the stars. So as you may have noticed that the comet actually moved a little bit. It was more centered, and it now has moved a little bit. because the comet is in an orbit around the sun. So you can actually see it when you're looking through a telescope. So I'm going to just move it over to the middle of the thing again, and you can see the tail again. It's so pretty. I mean, I could look at this forever, but you're probably wanting to see other things. So I will just play it just a little bit more, and then I'll move to something else. Okay, I'm going to take a screenshot of this as well. Okay. There's Comet Neowise. Okay, so what else did I want to show you? There's actually quite a few things I wanted to show you. There were a few clouds tonight, but I think they're mostly clear. So I think we're okay. I wanted to show you a few nebulae because they're so pretty, and summertime is the best time to see them. So one of the first ones I wanted to show you was something that I wanted to show you last Starry Nights, but a cloud was in the way. It was really annoying. It's called the Bubble Nebula, which is really cool. So let's move over there. The Bubble Nebula is in the north-ish. Where is it? There. And okay, so now I'm going to have to adjust this to be more like 60 seconds, and I'm going to live stack, but I'm going to, whoops, cancel. I am going to have to put in the darks and the flats. These are just post-processing, pre-processing. Usually it's post-processing things. These help improve the image. So I'm going to, okay, we're good. And we want a live stack of this nebula. Whoops, clear that. We don't want it on top of the comet. So, the Bubble Nebula. The Bubble Nebula is so pretty, it's so cool, and it's so cool that you can see it with this telescope in the middle of a bright city. It's called the Bubble Nebula because there's a nebula in it. Okay, let's adjust the image a little bit. It's not quite. Whoops! I'm gonna have to zoom out just a tad and adjust the colors. And adjust the black level. And let's see, we're not quite seeing it that clearly yet. Oh yeah, this flat is probably not the right one. Let me think, which flat was it? That one. I am going to clear this and try again. Okay, so you probably already saw the part of the bubble. The bubble, we actually can't see the entire bubble. We can see half of it though. Let's see it when it comes. So because it's a lot dimmer than the comet, obviously, so we have to have a longer exposure. So we're taking a 60-second exposure of the Bubble Nebula. And I'm going to try to stack, like take multiple images and do what's called live stacking in order to help improve the image, and remove the noise. And let's see. Yeah, I'm not using the correct flat. I apologize for that. I don't remember which one it was. But you can already see a little bit of the bubble in this image. I'm going to try to enhance it. And this probably needs to come up here. There, you can already see part of the bubble right here. Here we go. Okay, so let's stack the image a bit and see how that goes. Yeah, okay, so the stacking is going well, it's working, which means it just combines multiple images. So it's taking 60-second exposures multiple times and then combining them. And so here we see the bubble here. This star right here is the white dwarf that's blowing this bubble. So we're only seeing part of it, the brighter part of the bubble, but it actually goes all the way around. And actually, I believe we have like a better image of it from the Trottier Observatory using our more sensitive camera. Our more sensitive camera is much better than this one, but it's only in monochrome. So we have to take an image in red first, then green, then blue, and then combine them with colors later. The camera that we're using right now is a color camera, so I thought you'd be more interested in seeing color image instead of black and white images. So this is, but the downside is that it's a less sensitive camera, so it's harder to see the details. But at least it's in color. So Godwin asked, what is unique about the bubble? Yeah, so what's cool about this is that this star is blowing out the bubble. The bubble is a circle about like this, and it's completely lopsided. And the reason for that is because, okay, so the star is blowing out a stellar wind, just like the sun does, a solar wind, and it blows out, when that solar wind crashes into the gas that's already around the star, because this is a star forming region, so it's got a big cloud of gas and dust. So there's this gigantic, in fact it's called a giant molecular cloud. A giant molecular cloud on this side of the bubble, which is quite dense. And so when the stellar wind blows its wind out, it gets stopped on the side of the where it meets the rest of the cloud. So this part of the cloud is a lot less dense, so there's a lot less resistance, so the bubble can expand that way a bit more. And that's why the star is off center from this bubble. So I thought that was pretty neat. So a stellar wind, as I said before, it's like the solar wind. It's mostly electrons and protons, right? Negatively and positively charged particles. And actually, and as I said, it's the same thing that makes the comet tail. It's what makes the ion tail. So that's exactly what's happening here, except that this bubble is something like 7 light years across. So it's way, way bigger than the solar system, way bigger than this comet. So our solar system from the sun to Pluto is something like 10 light hours, right? It takes 10 hours for light to get from the sun to Pluto. So in case you were wondering, it takes 8 minutes for the light to get from the sun to Earth, and then it takes 10 hours for light to travel to Pluto. But this bubble is something like 7 light years across. So it takes 7 years for light to get all the way across. So this is huge. This is really huge. So you can see that stellar winds actually do affect quite a long distance. In fact, the sun's wind affects a really long distance. It took, so the Voyager spacecraft, which was sent out in the 70s to explore the Jupiter and Saturn, it was sent out to try to leave the solar system. And it still hasn't completely left the solar system. It hasn't completely left the influence of the sun. It's left one barrier of the sun, but there's the second one that it hasn't quite left yet. So, so the stellar winds from a star affects quite a large distance. Okay, so I said that this edge of the bubble is meeting the thicker, you can see a little bit of the giant molecular cloud here. You can see a bit of it here. It's hitting the denser part of the cloud, but you can also see this pillar here, and that pillar, it's a pillar. It's like a little finger of dense cold gas on the one side of the bubble, and it's actually kind of a cooler, denser hydrogen gas. And so it survives the blowing of the stellar wind, but it's still, so remember I said that one of the comet's tails is an ion tail. It means it's like a tail of charged particles. Well, in the same way, the wind from this star is also ionizing the gas in this finger. And so what that means is that it's stripping electrons away from the hydrogen. But the electrons eventually find its way back to the hydrogen atom. And when the electron goes back, it has to lose energy. It has to emit energy in a certain wavelength of light. So which means that it has to, when it loses energy, it emits light. And it has to be a very specific color that it emits in. So this pink is actually, it's not because I've done some weird thing with the color. Pink is actually pretty typical of hydrogen, because hydrogen, when hydrogen loses an electron and gains it back, it glows in this pinkish color. So a lot of nebulae that you'll see in astronomy images are pink, and that pink is because of hydrogen. I mean, a lot of times there's photoshopping and color, tweaking, but mostly the pink is from hydrogen. So that's what this is right here. It's glowing because of hydrogen. Okay, how's the stacking is going well. That's good. What are we? Oh, so another good question. Aren't the particles so far apart that should just go through? Yes, that's true. There's so when I say that these clouds are dense, they're not so they're still very not dense. So compared to the Earth, so the density within the bubble is like a few particles per meter cubed, but the density outside will be maybe like 10, like a few times more than that. So it's denser. So you're right in the sense that because there's so much space between them, it's not likely, like, how come they just don't go through each other? Well, they're still, because a meter cubed is still really tiny compared to light years, there's still a probability for like a non-zero probability that the gases will collide with each other. So gases, so it's really sparse compared to the Earth, but it's dense enough that they actually do affect each other in space. It's not like stars. Stars, meaning clusters of stars, have a lot more space between them than gases. Gases have like particles per meter cubed, whereas for stars are like a star per many light years, right? So this is the Bubble Nebula. What other questions do we have here? Oh, is that why the shot we're seeing is mostly pink in general? Yes, it's mostly pink because it's hydrogen. Hydrogen is the most abundant element in the universe. So a lot of things that are glowing are hydrogen. In fact, I remember when I was a couple of years ago when I went to see the total solar eclipse and the moon completely blocked the sun. It was so cool because I could see these little fingers coming out of the sun that were pink, and I was like, that's hydrogen alpha. I know exactly what wavelength that is. I was so excited. That was, it's pink. I know it's exactly the same shade of pink that you see in nebulae and in galaxies as well. It's because it's hydrogen. I just knew it, and it was exciting for a scientist. It's really geeky, I know, but it's also really fun. Okay, so what other questions do we have here? Yes, that's right. Most gases that are illuminated by stars is still hydrogen, because hydrogen is the most abundant element in the universe. The next most abundant element is helium, but most things are hydrogen. Okay, what are we at? Okay, we should move on. Okay, I wanted to show you a couple of other cool things. Okay, the Eagle Nebula. I'm going to try... You know what? I'm going to go to the Swan Nebula instead. So the Swan Nebula is... the Eagle... the Eagle is kind of cool if... Okay, let's do the Eagle. And if it doesn't show up very well, we'll do the Swan, which would be easier to see. So now we're going back to the south part of the sky in the constellation Sagittarius, near the center of the Milky Way. So actually, if you look towards the south, okay, I'm going to turn off the comets because the comets are a bit too crowded. So there's this constellation called Sagittarius, and it actually kind of looks like a teapot. Look at that. It's quite large in the sky. It's in the south. In Vancouver, it's very low in the south. You have to have a clear horizon in order to see it. But in other parts of the world, it gets quite high. So the center of the galaxy is around here, close to so the teapot there's like a black cloud. It's quite large. You can see if you're out in the countryside and you can, away from the city lights, you can see the Milky Way really, really bright all around here, and this dark spot here that kind of looks like, steam coming out of the teapot, which is kind of neat. Anyways, the center of the galaxy is approximately over here. The galaxy, you can when you see the galaxy, okay, what is a galaxy? The galaxy is just made of 100 billion stars. So our galaxy is called the Milky Way. We're inside of the galaxy, so we see, when we look through, like the galaxy is like a plate, right? And if we're a really tiny speck within the middle of the plate, we see some plate above us and some plate below us, but most of the plate will be like towards the center of the plate, right? It'll be in a line like the Milky Way is. So the Milky Way actually goes through Cygnus the Swan and Aquila the Eagle and Sagittarius, and it kind of goes across like this. In fact, it goes all the way around the sky because the Milky Way is a plate, like a disc. And that's where you'll see most of the nebulae. So we looked at one that was also on the plane of the Milky Way, but you'll see actually in this app, you can see a lot of nebulae that are just listed all along the Milky Way. That's where you'll find them. Star-forming regions are always found along the Milky Way. Okay, so now we are at the Eagle Nebula. Did we slew there already? Yes, we did. And let's clear that. And let's take a look to see if we can see the pillars. The Eagle Nebula, there was a very famous image from the Hubble Space Telescope very early on when it was launched, and it was called the Pillars of Creation. It's so beautiful. We'll be able to see it as well from here, and hopefully this will work. Yay, there it is. Okay, do a little bit more adjusting. And there it is. There is the nebula. So it'll stack, hopefully, and clear up some of the noise. And so you can see these three pillars here that formed the basis of why the image was called the Pillars of Creation. So it's pretty cool. As you can see, it also glows in pink, so that I know the color isn't great right now. How do I adjust it better? I think if I do this, yeah, that's better. Maybe a little bit more this way. There it is. This is the Eagle Nebula, also known as Messier 16, M16. And yeah, Pillars of Creation right there. This pillar here is, this whole thing, again, nebulae are really large. So the bubble nebula we saw was 7 light years across. This thing is about 9.5 light years long. So, as I said, clouds like this, like a nebula, is the site of new star formation. This cluster here is associated with this nebula. And it's got about 8,000 stars associated with this nebula. So stars are formed out of the gas. So the gas condenses due to gravity and it becomes really hot and starts to ignite nuclear fusion, which is the fuel for stars. And it's why stars shine and why they're hot. So all of these stars are associated with this nebula, and you can see that there are actually a lot of little clumps in here where we think new stars are being born right now. The pillars are being blown away eventually by these hot stars. In fact, these two, I think it's just this one actually. This one is this star right here is called a hypergiant. It's actually really rare to see hypergiants. There aren't very many of them, but they're extremely massive stars. It's probably about 80 times the mass of the sun and about 1,000,000 times brighter than the sun. So it's called a hypergiant. But if you see a giant star like that, or any kind of blue hot stars, then you know that the cluster must be young. And the reason is because we're assuming that they're all forming about the same time. And the really bright blue ones, the most massive ones, they don't live very long. They only live for 1,000,000 years, maybe maximum 10 for the smaller giants. This hypergiant will not live that long. Something like 1,000,000 years, which is considered very short for astronomers. And so if you see a cluster with bright blue stars, you know it can't be older than 1,000,000 years, because a star like that will have gone supernova if it was older than that. So clusters like this are important for understanding star formation and actually for understanding galaxies and how galaxies form. But we don't have to go into that today. Maybe if we get a chance to look at another galaxy, I might talk more about that. But this is a star cluster, and this is a hypergiant. Is it stacking? Oh, it's being ignored. Too bad. Let me see. Well, that's okay. We spent a long time on this. We only have half an hour left, and there were a couple of other things I wanted to show you. So this is a site of stellar birth, and I wanted to show you a couple of other things. The Swan Nebula would be really cool to see. Oh, this is really too bad. It's not stacking. Well, that's okay. We actually see it. We still see the pillars quite well. Let me remind myself what the settings were for stacking it properly. So this app is a really great app. It's called SharpCap. It's actually really inexpensive as well. If you have a camera that can do this kind of thing, and a telescope, SharpCap, it's usually very good, but you have to fiddle a lot with the settings for alignment here, and I made sure I wrote down all the settings, and which worked really well for this nebula. So I'm just gonna go check what settings worked best for this nebula. Let's see. M16. Oh, and these were exactly the settings, so I'm not exactly sure why it's not working. Maybe I'll clear it again and see. Unless you would like to see something else. Let me see. Okay, we do at least have a request for one galaxy, so we could see a galaxy tonight. I'll make that more of a priority. What else? Yes, that's right. If we have time, we may look at the Andromeda galaxy. Okay, let's see how this galaxy or this nebula turns out. we could look at, in the meantime, the other one I wanted to show you. We can skip the Swan Nebula. The Swan Nebula also has 2 hyperstars in it. Crazy, 2 hypergiant stars in it. So this is a hypergiant, and there are 2 in the Swan Nebula, which I can show you if you want. And I just told you that hypergiants were rare, but you expect to see them in nebulae because that's the site of new star formation, especially young nebulae, because hypergiants don't live very long. So you have to have a young nebula in order to see one. And okay, let's see if this first one stacks, or the second one stacks at all, and if not, we'll just move on. And in the meantime, any other questions that did not get answered? How noisy is the waveform of light coming from far away? So the noise comes from the detector. Actually, the camera has noise in the pixels, as well as there's noise in the atmosphere. So light pollution from the city is a major problem. It actually causes, the light pollution from the city actually causes the sky to glow in certain specific colors, in the same way that the sun causes the comets to glow in certain colors. The atmosphere glows in certain colors because of the city, and it's a major problem. But what can you do? And that's actually we could see quite a lot, given that we're in the middle of a big city. Did it stack? It didn't stack. Okay, so we'll move on to something else. In fact, I'm going to skip the Swan Nebula because it's basically, the Swan Nebula is another nebula that is a site of star formation. But not all nebulae are sites of star formation. There are also nebulae that are sites of stellar death. So I'm going to show you one called the Dumbbell Nebula. And this is one that we did see last time, but it's really pretty, and I know a lot of you are here for the first time, so I'm going to show it to you anyway. And it's a really pretty one. So it's got lots of cool colors. So as soon as the dome moves over, yes. So as soon as the dome moves over, we can see it. And it's probably not going to see it all because might have to restart this one. Yeah, I'm going to restart it. Okay, yeah, so not all nebulae are the sites of stellar birth. There also, some of them are sites of stellar death. Now, why is that? It's because, so most of the time, so when I showed you the Eagle Nebula, those pillars are actually being blown away eventually. So the really bright stars that were to the upper right, that cluster of stars, they're all blowing stellar winds, just like the sun is. But especially the massive ones are blowing huge stellar winds. And they're eventually going to blow away all those pillars. So in something like 100,000 years, those pillars will disappear. And the nebula will disappear. But, however, no, we still don't have anything yet. However, a star, once it gets to the end of its life, it turns into a red giant, and then the red. So there are lots of reasons for it exploding, or not it's not exploding. So galaxies, or sorry, not galaxies, stars that are about the same mass as our sun will expand into a red giant, and the outer layers of the red giant will eventually float away into space. And when they float away into space, they form a nebula. But they form what's called a planetary nebula because they're round usually. Okay, so apparently we have a nebula, but I do not see it. Let me see what's going on. Wait, here, oh, that's why. There we go. Ah, there it is. It's so pretty. adjust it a little bit more this way. Look at that. Oh, so beautiful. I know I showed it to you guys last time, but I can never get enough of it. Look at these colors. So here, so again, pink. What's pink? What element is that? This is called the Dumbbell Nebula, by the way. This is M27, Messier 27. What's pink? Does anyone remember? What does pink mean? Hydrogen! Yes! People got it. Okay, there might be a little bit of a delay between my voice and your comments because the internet, you know. So, yes, pink means hydrogen. And blue, in this case, I told you blue before. Oh no, I told you what green was. Comets have completely different elements than nebulae. But in any case, the blue here is oxygen. So what's the star here in the middle is a white dwarf. So what happened here is that at the end of its life, it expanded into a red giant, and that red giant floated away. The outer layers floated away. So when a star dies, it means it's converted the hydrogen that's in the very center, the core of the star. All that hydrogen got converted into other elements like oxygen. But that only happens in the center of the star because that's the only place where it's hot enough to do that. All the outer layers are still hydrogen. And so that's why they're red here. So the outer parts of this nebula are red because that's the outer layers are hydrogen. But the inner parts are blue because that's where the hydrogen got converted into things like oxygen. And that's why it's blue in the center. And that's why this type of nebula, which is the site of stellar death, has different colors like that. And this is probably what will happen to our star as well, our sun, near the end of its life, in something like 5 billion years. So you don't have to worry, it's going to take a while. Okay, so let's adjust this a little bit. Oh, so pretty, look at it. Yeah, I can never get enough of these images. They're really, really pretty. And it's stacking properly, so this is good. So this nebula, so I told you the sites of stellar birth are something like, tens of light years across. The Dumbbell Nebula is more like 3 light years across. So it's smaller than stellar birth. They're usually quite large. Tens of light years. So the little Eagle Nebula, that one pillar was about 10 light years long, but the whole nebula was quite a lot bigger than that because it's creating lots of stars. This is the site of the death of one star, so it's only about 3 light years across. Our solar system, again, is something like 10 light hours, so our solar system will be much, much smaller than this. But the nebula itself is expanded into about 3 light years. Anything else I can tell you? Oh yeah, one thing that's cool about this is you can look at the shape of this. So it looks like it's a dumbbell, right? Like it's a little bit lopsided where the gas, there's a lot of gas on these two sides, but not as much on these two sides. So it's like it's one of the type of nebulae called like a biconical nebula, which basically means the nebula floats out in 2 regions. That's what it means. It's just 2 parts. And it goes out in 2 directions, and it's not really clear why that is the case, but one of the most likely reasons is because there might be like some sort of disk of material around the star so that it's much easier for the gas to go above the disk or below the disk. So the disk of material like an asteroid belt or a Kuiper belt or planets even. Might be the reason why the nebula has this shape. The star in the center is a white dwarf. It's very hot, so it hasn't really. A white dwarf is completely made or almost completely made of carbon. It's still very hot. It's no longer burning fuel. It's not turning carbon into anything else. It's completely done, but it's hot, and it'll take a long time for that heat to radiate away. The sun will probably become like this, become exactly like this nebula actually. So that is the Dumbbell Nebula. So it's stacking properly, so that's good. So the image is getting better with every stack. So this is really pretty. I am going to save the screenshot and save these as well. Okay, we are going to, in order for me to show you a couple of other things, I should probably get going. Let's see, we've got, there's several things, several cool things to see still. We've got 15 minutes. I can show you the Andromeda Galaxy and Jupiter and Saturn. Do we have any preferences? I know at least one person voted for the Andromeda Galaxy. Jupiter and Saturn are also really cool. That's going back to our solar system, but I will wait for any preferences. Okay, I have another vote for Andromeda. Let's see. Okay, and yet another one. Okay, let's look at the Andromeda Galaxy then. So, as I said before, so everything that we've seen so far has been within our galaxy. So we've seen the moon and the comet. Both of them were actually in our solar system. They were really, really close by. And then these other nebulae that I showed you were something like a few thousand light years away. So thousands. Our galaxy is about 100 billion stars. And the galaxy is about, in terms of diameter from end to end, it's probably about 100,000 light years across. Okay, it's like, so as I said, the Milky Way is like a disc, like a plate. And we're kind of, if you take the center of the plate to the edge, it's like 150,000 light years, right? We're somewhat in the middle, between the middle. So between the middle and the edge, we're halfway between the middle and the edge of the plate. That's the Milky Way. The next closest, the nearest galaxy to us, there are lots of galaxies in the universe, millions, billions, in fact, billions of galaxies in the universe. That's how big the universe is. It's enormous. The nearest large galaxy to us is called the Andromeda Galaxy, and let's go there. Okay, so I'm sorry I keep talking and not showing things. So there's the Andromeda Galaxy. You can actually see it with your naked eyes. It's the farthest thing that you can see with your naked eyes. It's pretty cool. You can see it in a dark. You have to look in a dark site. You have to go to away from the city in order to see it. Unless you have binoculars or a telescope, then you can see it pretty easily. It's a really bright object. In fact, it's quite large on the sky. It's definitely much bigger than the camera's field of view. But we'll see it once the dome moves over there. Okay, there it goes. Oh, that's so pretty. Okay, I've already taken shots of this. Okay, but let's take a look at the Andromeda Galaxy. So the Andromeda Galaxy is about twice as massive as the Milky Way. So it's more massive than the Milky Way, and it's about 2 million light years away. So we'll look at more the center of the center of the Andromeda Galaxy is the brightest. So there it is. Let me adjust it a little bit. That's the center. And that's the center of the Andromeda Galaxy, and the galaxy is way bigger. It's bigger than my screen, definitely, by this magnification. There's an amazing image taken by the Hubble Space Telescope where the Hubble could actually see individual stars within this galaxy. It was amazing, and you could see that the center had like a ton of stars. They were really, really dense. You could hardly pick them apart. But when you went out to the edge of the galaxy, there were a lot fewer stars, and you could pick them apart. and you could see a lot more space between them. So galaxies actually have this, what's called an exponential profile, because the numbers of stars from the center to the outside decreases exponentially, because there's an exponential decrease in galaxies in the number of stars. And so that's one of the things. A lot of, at least spiral galaxies have this exponential decrease. And there are different types of galaxies. The Andromeda is a spiral galaxy. The Milky Way is also a spiral, so we've got 2 spiral galaxies in our local group. But there are other galaxies that are more round, and those are called elliptical galaxies. The local group of galaxies consists of 2 large galaxies, so we've got Andromeda and the Milky Way, so we're a bit of a pair. But we also have a whole bunch of little galaxies that we call dwarf galaxies that are orbiting around us. The Milky Way has something like 20, and Andromeda has something like 20, and all together, this group of galaxies is called the local group. Yeah, let me adjust this a little bit more so you can see some of the detail. What's really cool is that you can see some of the dust lanes in this galaxy as well, up there. So we're kind of looking at it such that, so the galaxy is tilted, so it's also like a plate. The Andromeda is also like a plate, but it's tilted towards us such that this edge is closer to us, and this edge is farther away from us. The edge, that's the way we can tell, is because of the dust, actually. Because the more sideways you turn a galaxy, the more dust you're looking through. It's just like the atmosphere when we were looking at the moon earlier, and when we're looking through more atmosphere when it's lower in the sky, kind of for the same reason, similar reason at least, the disk of the Milky Way, when we're looking through when we turn the plate so that we're looking along its edge, then we're seeing a lot more dust. And so the dust, so that's why we can tell that the dust here, it's also blocking light from farther away, right? So the center of the galaxy is farther from us than the edge that's closer to us. So the dust is blocking light from farther away. So the dust that's on this side of the galaxy isn't blocking light because all the light is from closer to us. I don't know if that makes any sense. But anyway, that's how we can tell that this edge is closer to us. That's one of the ways, at least. Yeah, so this is pretty cool. So I think somebody already mentioned that the Andromeda Galaxy is going to collide with the Milky Way at some point. It's in about 5 billion years, approximately the time when the sun will die. So, but when the Andromeda collides with the Milky Way, it's not really like if we pretend the sun will continue on, live longer, and the Earth will continue as it is. The collision of the 2 galaxies will actually not affect us. It will, because there's so much space between the stars will just pass each other and nothing will happen to the Earth. It's kind of crazy. But we'll see this big, like most of the stars in the sky will be red instead of blue. Because a collision of galaxies is one of the ways, at least in simulations, we see that new star formation tends to stop after a galaxy collides with another one. There's lots of reasons for that. I don't have to get into it. But yeah, so yes. So somebody else asked that, is it true when the Andromeda and Milky Way merge, there's very little chance of any collisions of stars? Yes, it's true, because there's so much space between the stars. There's that the chances of collision are just really, really tiny. Yeah, so there's the Andromeda Galaxy. So I love galaxies, as I said. Galaxies, I know that different people are probably tuning in at different times, but I mentioned earlier in this broadcast that my research is on galaxies, and one of the reasons why I like galaxies is because you do have to know something about little small things like stars. Stars are considered small in my field, and big things like the universe. So it kind of is a bridge between the fields of stellar astrophysics and the field of cosmology, which is the field that studies the universe as a whole. So Yeah, actually one of the things that I study about galaxies is why they stop forming stars. So there are galaxies that are like the Milky Way, that there are lots of little nebulae, they're all still forming young stars. You can see these really blue, hot, giant stars that are really, if you see them, then you know they must be young because they don't live very long. And then so there are galaxies like that, but then there are galaxies that are round and all the stars are red. There are no young stars to speak of. So those stars they're called red and dead because they're no longer forming any new stars. And one of the research questions that I study is why that is. Why is it that there are two types of galaxies? We expect galaxies to form stars because there's so much hydrogen in the universe, and hydrogen is the fuel for star formation. So why is it that some galaxies have completely stopped? We find that the ones that are dead don't have any gas anymore, but what removed the gas? Like why is there no more gas in these galaxies? You know, these are the types of questions that I look into. Oh, how do we know that they are dead and not just redshifted? That's a good question. Well, it's because we can measure the redshift of these galaxies. So what is the redshift? That's a very good question. Okay, so when we observe light from a galaxy, we can split it up into all its component colors. So we can split it up into like red and a little bit less red and a little bit less red than that, and orange and yellow, and we can split it up into basically really like small bins of wavelength. The colors are wavelength basically. So when we do that, we can easily measure we'll see a lot of lines like so hydrogen, for example, will glow at a very specific color, which is a very specific wavelength, and that hydrogen will tell us if it's moving away from us or moving towards us, and if it's moving away, it's redshifted because light changes color when it's moving away from us. But the galaxies that are red and dead, they're not like they're not. You can measure their actual redshift, and they're not moving far enough to account for their red color. The red color, the reason why they're red is because of the stars. It's not because of the redshift, because the redshift really is a small effect, just tiny little effect for these galaxies that we're talking about. Okay, great questions, everyone. Thanks for asking them. So this was the Andromeda Galaxy. Okay, we've got a few minutes left. Does anyone want to see Jupiter or Saturn? Actually, this is really funny. Let me save this. Okay, there we go. I've saved it. So pretty. Oh, yes, sorry, I confused you. Why are dead stars red? So the stars that are red are not dead. They're still burning hydrogen, but the galaxies, I'm calling the galaxies dead rather than the stars. If they're full of red stars, it means that if they're red stars, it means they're not the ones that are short-lived. They're the ones that are really long-lived. So it means that if you only see red stars, it means you're not seeing any blue stars, which means you're not seeing any more new star formation. So in order to have blue stars, you have to have new star formation because blue stars don't live long enough. So if you see a blue star, it means you've had very recent star formation. Okay, so we have a couple of votes for Saturn and one vote for Jupiter. Okay, so we have a lot of Saturn requests, so I'm going to go to Saturn. And Saturn is pretty cool because it's got rings. So let's move there. Saturn's in the south right now. I just moved to the southeast. They're actually, both Jupiter and Saturn are visible to the naked eye. They're really bright. They're brighter than most of the stars. In fact, Jupiter is brighter than all the stars, and Saturn, I believe, might also be. There might be one or two stars that are brighter than Saturn. But anyways, Jupiter and Saturn are extremely bright. Definitely you can see them in the middle of the city. They're in the southeast right now. Jupiter is a little bit brighter than Saturn. And let's just take our last minute to take a look. Oh, I have to, this has got to be a much shorter exposure. Whoops. There it is. It's got to be a shorter exposure than that. Even because it's so bright that, oh, no stacking. There it is. Is that cool? You can see the rings. Okay, I am going to not bin, and I'm going to show you the planet a little bit closer in. Okay. There it is. Okay, let's adjust it a little bit. And I probably need a even shorter exposure than that, actually. There. Okay, so look at that. You can see some of the bands around Saturn and the ring. There's a gap in the rings, actually. This is pretty cool. So Saturn is the second most massive planet in our solar system. And fun fact, it's actually less dense than water. So if you had a gigantic bathtub and you threw it in that bathtub, it would actually float, which is kind of fun. The rings are huge. The rings, actually, the distance between the edge of the ring to the other edge is about the distance between the Earth and the Moon. But they're really, really thin. In fact, the rings are only 20 meters thick. It's crazy. They're incredibly thin. I was so shocked by that statistic. I only read that recently, to be honest. The rings are mostly made of water ice with some rocks, and you can see. So Saturn has something like 82 moons. It's incredibly. There's a lot of moons, but there's some of the moons actually live in the rings. As you can see, the Saturn is actually quite low in the sky, so there's a bit of atmospheric turbulence here that you can see. But you can sort of see a gap in the rings here and here. And one of the moons actually lives in that gap. It orbits the planet in that gap and helps maintain that gap. And there are other moons that actually, they're called shepherd moons. They keep the rings from spreading out. So yeah, some fun facts about Saturn. All right, we're a little bit over time now. Thank you so much for joining me. Thank you to Matthew, Zena, and Sarah for helping to answer questions. This has been really fun. I'm sorry I haven't been able to answer as many questions as I would like, but thank you so much. And if you would like to ask any more questions later, please feel free to email. My email is on my website. And yeah, there we go. This is Saturn. Actually, I'm going to take a screenshot of this as well, because this is really cool. This is really pretty. Yeah, okay, I already took a screenshot. That's good. Thank you very much. Good night. Keep looking up, and we'll see you next time. Good night.